All right, so topic of today is beginning, I suppose, of congestion control. Before that, I wanted to talk a little bit about the homework. So I'll put up my node running after class today. It's finally running. I've been dealing with admissions in the last week, and there's like 1,250 applicants that I'm one way or another in charge of. So that's what's kind of been holding me up. For graduate school only, not the undergrads. All right. So there were a couple of things that I ran into while I was making this homework solution, little clarifications. Let's see. One was to do with the load balancing. It gets really weird. Yeah.
Can you turn off one of the lights?
Yes.
Hit
the projection mode. All right. Yeah. So one has to do with the.
So will you be recording?
I am recording it. Yes. One has to do with the load balance message. Right? When you send a load balance message, you have to pick like which peer should we rebalance to, or it's called a rebalance message, right? So if you were to pick just one peer, always the same peer, you would likely run into some trouble. At least if you don't eliminate the upstream peer as an option. So you could imagine, we go like this. Let's see. All right, so I got one peer, and I'm connecting another peer. All right, and I'm connecting another peer. And now we want to tell this guy, like, oh no, you can't talk to me. In fact, let's have one more. Let's have an upstream as well. This one was connected to there before. All right, so these arrows indicate like which one I connected to. Like on the command line I specified, talk to this peer, let's say. Or perhaps as the result of a failover or a rebalance. Okay, so in any case, say this node now wants to tell this one to rebalance because it only wants to have one child. It could, conceivably, tell it to rebalance to upstream here. But if you allow that, now the upstream only wants to have one peer as well, so it'll rebalance to its only other peer, the child. Right? And now I'm going back and forth, and that's no good. Right? So there's two reasonable solutions here. The better one would be to pick a random peer. So you just pick one of your other peers and say, go see that one. And that one will say, no, I'm not interested, like go see someone else. And after a while, you might bounce around a little bit, but at some point you'll end up in one of the leaves, right? You'll end up down here, and that's okay. At some point, there's always going to be someone who doesn't have any children, and we're okay. Of course, having a maximum out degree of 1 means we're always going to have a string like this. That's actually kind of cool. Make a nice little string network. Okay, so that's one. I would suggest picking a random peer. In principle, it would also be correct to always pick a downstream peer. Right? If you pick an upstream peer sometimes, and that one picks a downstream peer, that's really not going to work. Everyone can't pick all upstream because then at the top there's nowhere to go. So always picking downstream would work. Random would make for a much nicer network. All right, and then there was the failover. Yeah?
I was just going to mention, the homework write-up says that if you're upstream, you always have to pick a downstream.
Does it? Okay, well, it's been a while since I wrote it. Okay, so for rebalance, you always have to pick a downstream, it says. Okay.
If you have it upstream.
I don't know that. Okay, we should probably take a look, make sure we're talking about the same thing. So there's the failover and there's the, let's see.
Oh, maybe I am talking about the failover.
Yeah, they could be. But why don't we look at this, and I'm going to update the description a little bit. All right, so where is it? Right, load balancing. to some of its downstream peers. Okay, right. It would be fine to go with a random too, but you cannot go like have a node that always ends up going to the upstream. Then we would definitely have a problem. Okay, so for the fault tolerance, yeah, I think it's in order to guarantee correct operation here, whoever is recommending a failover peer really should check them first. Right? So I think we discussed in class before that, if you're told this is a failover peer, try connecting to it first before giving up on your connection. But it'll be much better if the node that is recommending, that's saying this is your failover node, has checked that this is a valid failover node. The problem that you may run into is that it's not possible to reach that node. The node is able to connect to an upstream peer, but a peer somewhere on the internet can't connect back in because of various firewall rules and network address translation. So really, we should verify that when a node specifies, I'm a new peer, I'm on this port, we should go and check that. It's easy. Connect to it, see if it connects, then disconnect again, and fine. So that's what I would suggest. All right, so one test case that we'll certainly do for fault tolerance is we'll start 3 nodes, like a root, one connect. Okay, I'll do it on here. So here's a simple failover case we'll test. We'll start 3 of them. We will connect like this, and then we will kill this node also, and we will specify to this one that your failover peer is over here, right? And then we will kill this node, and any telnet client connected to here should be able to see any messages that are sent from a telnet client connected to here still. Yeah.
So when we're testing to see if you can connect to a peer, will we just try to call connect with a timeout parameter?
Yeah, that's fine. Yeah.
So for test cases, in Hamidson and Piazza basically so when you're forwarding a message or something you're propagating across the network, you need to make sure that you're not sending the message back to the person who sent you the message.
Right.
Which makes sense.
Yeah.
My question is, should we account for a test case where you have a ring of nodes?
You don't need to, because it's not possible to create a ring.
Well, if each one just connects to one, like a string, but you just connect the ends.
How do you connect the ends is the question.
Well, would that one just have it
So the thing, the way we have all this set up is you always have one upstream.
Okay.
And so you only ever connect to one other node. So if you wanted a ring, so say we have these, this is what we're talking about here, right? So now you want to get a connection from, so this was the root when we first started out.
Yeah.
Right. So it's not, the root isn't going to connect to anyone.
Okay.
Because it started out without anything specified. This one started out with something specified, so it's not the root, so it'll, it could potentially have to connect to somewhere else, right? But it's not, now it disconnects from, we end up with a tree just by sort of, it has to be like that. Yeah. So I wouldn't worry about it. But yeah, if you run into a situation where you have a ring, then something's weird. Oh. Any more questions somewhere in the back? No. All right. Yeah.
So the root only gets a message if one of its clients wrote the message?
Yeah, if one of its telnet clients wrote the message, or if any of its peers delivered a message to it. Yeah, okay, so the root, sorry, this is not how you forward messages. You don't go always up to the root, right? You forward to all your peers, except the peer you got the message from.
Okay.
So in this case, it'll just go up. In this case, it'll go just down here, right? And so on. Yeah, there were more questions. No, that's it. Yeah.
Could you conceivably, I haven't thought this through enough, but could you, since we can have multiple connections, is it possible to end up with a ring? Even if you, I haven't thought enough about it, but or like a result of load balancing. I don't know if it's possible. I'm not.
I don't see it. I don't think so. If you can think of one, it'd be very good to let me know. We'll try to resolve it. Yeah, this was a surprisingly challenging homework to describe, it turns out. I don't think it was very complicated to implement. It's just a few messages sent here and there. But I can understand when the description isn't crystal clear, it gets harder that way. It'll get interesting. Once my node is up, I think that'll also help a little bit. You try talking to it, and it turns out it doesn't quite work the way you thought, and then take it from there. One thing to note, port here is a network byte order. That's always the case whenever we transmit any sort of numbers over the network. We send everything in network byte order, which means it's the opposite of host byte order on the Intel, which is little endian. Right? So this is big endian. There's a handy little function called let's see, network byte order H2NS is the one you want for now. Host to network byte order short, like 16 bits. Okay. Anyone want a quick review of byte order? We got one. All right. So the principle is bytes, we don't worry about the order of the bits. That's always, that's not something that we see on a protocol level. But if you need to send something, send a number that's more than 1 byte. Then you could potentially send the less important bits first, and then the more important bits, or the more important bits first, and then the less important bits. This is also something you would observe in main memory. If you look at what's in memory, if you have an array, you say like this, an integer which consists of 4 bytes. Now the question is, like, integer 0, is that the most significant bits of the 32-bit number or the least significant? All right. So on Intel, it goes, it's called little endian, and it doesn't, strangely enough, mean that the little part ends the message. Right? It's the little end first. You would think like little at the end, but no, it's little end first. So, so in Intel case, it'll be this is integer 0 is the little end of the message, right? Integer 4 is the 3 is the big end. Yeah.
Why do they pick little endian to begin with? Wouldn't it just make sense to go on order?
I think for a network, it makes sense to send the first byte that comes in is like sort of the high order byte. That seems to make sense because you want to kind of have the sort of the magnitude of things first, and then you get the little details after. But addresses, usually you start a data structure at address 0, and then you go address 1, address 2, address 3. See, where was I going with that?
Maybe there's no good reason.
I thought I had a good argument for it, but I lost it. It may have to do with compatibility. Maybe they figured, okay, we have everything working for 8-bit stuff here. So you're pointing at the value for the 8-bit integer, all right? And that's the beginning, that's address 0. And then, oh, I want to make it a 16-bit integer, so the 8-bit layout should be the same, and then the 16-bit can be different. Maybe that's it. All right? It could be like the addresses of, yeah. Like the location of the lower order of those first 8 bits don't change for various types. That's nice, maybe. I don't know, it's a stretch. Don't ask me. Okay, anyway, we use H2NS or H2NL for 32-bit numbers. Right? So this is actually relevant here because when you want to connect to port 8080, you have to say H2NS 8080. The port is specified in network byte order. And same thing when you pass around the ports in the failover and the load balance messages should be in byte order, network byte order. Okay, so we were supposed to talk about congestion control, so let's do that. All right, so I showed you this thing last time. And it's a very big abstraction of how things really work, so I thought we'd drill into it a little bit just to kind of understand what's going on, or the sort of the motivation behind our congestion control protocol. So more specifically, that looked like, we have entire countries in there, but more specifically, if we're speaking about a smaller network, we have our end host, our origin. We may have a couple of intermediate routers. And then one destination. And I think we may want to have, why don't we do origin source 1 and a source 2. All right, and then over here, destination 2. Yeah, we'll start like this. Okay, so what we're looking at is probably then source 1, this is a computer, this is a router. A router is basically a network. A computer sits in a network, it has lots of network interfaces. There can be some special hardware in the router, but you can make a router out of a Linux box with a bunch of network cards. That's a perfectly fine router. If you wanted to go a little faster, maybe you want some specialized hardware. Okay, so in general, we have some sources. We call these flows, a source-destination pair. Right? We're wanting to communicate from this source to this destination. We're only interested most of the time in one directional communication. Yes, there are some acknowledgements going the other direction. Let's not worry about them. So we have one flow of communication going from source 1 to destination 1. In fact, let me add a different stroke. Where is it? Right? And then we have another flow going this way. Right. Okay. So congestion control is this idea of not sending too much. It's unlike the highway. In the highway, you notice when you drive onto the highway, you can't get anywhere. That's because the highway is full. And you don't end up like cars falling off the highway left and right. They just kind of wait until they can go again. That's not the case with the network. And there's good reasons for that. In the network, the link itself can lose packets. Right? Depending on what kind of link we have, it could be a wireless link. They can be a little unreliable. But even on a wired link, every now and then maybe a bit flips. Like the transmission kind of fails a little bit along the way, and the packet is received on the other end, but with one bit wrong, this is detected using a CRC, an error detecting code, and the interface will just reject that packet. It'll not say anything, it'll just drop the packet. So that's one situation, and let's not worry about that one. That's the transmission errors. They're relatively unusual, except for on wireless links where they're very common, but we'll deal with that at the link layer a few weeks from now. The other cause of loss is congestion losses. So inside of each one of these routers, for the purpose of this discussion, we can think of it as a single queue. Right? Because we only have one outgoing link. Usually there would be perhaps one queue per outgoing link. Let's think of it as a single queue for now. There's many different ways to implement it, actually. Okay, so this queue has a fixed length. Packets come in at some rate. Let's see, in 1. And then we have packets coming in at some other rate, in 2. And then they come out here at some other rate, right? So generally speaking, if in 1 plus in 2 is greater than out, then the queue length is going to grow, right? Queuing theory 101. If you can't service your packets any faster than they come in, they're going to have to wait. That's fine. So you start out with a few packets, they come through fine. At some point, okay, they start coming in a little faster than the output speed. So now the queue builds and builds and builds. Actually, I can draw the queue like this. So we end up with an empty queue, and the queue just grows and grows and grows. And at some point, you end up running out of queue space. So now we have a choice. We can either drop a random packet from inside the queue, or we can drop the incoming packet, but there's nothing else we can do. Like, we have to drop a packet. It's the new one or it's an old one, and that's it. I guess there's a reasonable argument for either. You could also argue about which order you should be serving packets in. Right? You have a long queue here. If you pick the one at the head of the queue, that's fair. That's kind of nice because now, well, usually being fair is nice. On the other hand, you know that's going to be an old packet. Right? Whatever's been sitting in a queue for a while, that's an old packet. And if your protocol or your application depends on these being new packets, and it doesn't really care about old packets, then it'd be better to pick stuff from the end, because those are the newest packets. So you could serve in FIFO order, first in, first out. You could serve in last in, first out order. Last in, first out is really good for real-time sort of communication. For a voice communication, you probably want to do it that way, because it's really annoying with old packets in voice communication. You get all these delays, and nobody cares if you lose a few packets. It sounds like a little glitch, but it's fine. In either case, virtually every router out there will serve in FIFO order, because last in, first out is just weird. You get in the queue, and what? Everyone else behind you goes before you. It's just not right. Okay, so we end up with a full queue, and we start losing packets. That's what we call congestion. I guess there is some sort of congestion signal even before then, right? The longer the queue, the longer the wait. So a packet comes in here. It takes some amount of time to go through this link. And then it sits in the queue for a while at this router. And then it goes on the next link, takes some time to go across the link, and then the next router, and so on. So you could say there's congestion if the queue is longer than 0, right? Then now you end up with packets waiting. Waiting isn't any good. Interesting trade-off there. Why do we have queues at all? The problem is, these two might send a packet at the same time, right? So now you're going to have to drop one of the two if you don't have any queue. So at least you have to have one, like a buffer of length 1 for each incoming link. All right, so now we have a queue of sort of length 2. But then you could also end up with some bursty traffic. Like for a little while, someone sends like 15 packets back to back. I don't know what was going on, but they sent a lot of packets, and then they do nothing for a while. So a queue allows you to kind of spread out that load. Rather than dropping all those 15 packets, we wait for a couple of milliseconds, and now all of them made it through. So we get to have much more efficient use of the outgoing link. Yeah.
When a packet is dropped, does the router have to send a message back?
It doesn't tell you anything. It's up to the transport protocol, if it cares, to try to detect that. So with the protocol we've been discussing, that's what the acknowledgements are for. Send an ACK packet back. Other protocols don't care. If you're Skype, you don't necessarily care, because by the time you can retransmit the packet, it's already too late. You don't want to hold up the whole picture just because you lost a little bit around the eyebrows. So you'll just leave that alone. And yet other protocols really care very much about getting every byte through, but they cannot handle the round trip time. And that'll be, say, if you're sending packets from a Mars space probe, right? That whole acknowledgement thing is just too slow because it's such a long round trip time. Then you have to send with an error correcting code and stuff. So you send extra packets. You could imagine sending the picture twice, and then most of the errors will be fixed in one or the other. And we can maybe talk about error correcting codes a little later. Okay, so the very first thing we want to do is, in this communication, right? We start our flow. If there's nothing else going on in the network, then all the queues are empty. Let's maybe have another queue here. All the queues are empty, and we can start transmitting. But as we discussed last time, we might have a couple of fat pipes here, and then there's a thin pipe in the end. So now, if we're transmitting at full speed, whatever our outgoing network interface allows, that'll be fine. It'll actually pass through here just fine. And then we get to here, and now this queue will quickly grow, and then it's eventually full, and we start dropping packets, even though it's just us. So this isn't really congestion control in the classical sense, because there's no one else there, but it's maybe what do we want to call it, a capacity estimation. Like this, what is the capacity of the path to our destination? So one good way of finding that capacity I guess you could imagine a protocol where you can actually ask the routers along the way, like, how fast is the next interface, right? So you check all of them, like ask this one, and then you just take the minimum of them. This would actually work quite nicely, but of course only if no one is using the network, which usually isn't the case. And it also requires some intelligence on the part of the routers. They would need to know what is the capacity of this link. They need to be able to answer and so on. So extra complexity in the routers makes them more expensive. And it's not always clear that you know what the link capacity is. That could depend on environmental conditions, that sort of thing. So in the end, the internet doesn't do that. We just don't say anything. We leave it to the end hosts. A good way to estimate it might be to start slow. Start with a little bit, right? Whatever that means. And then after one round trip, we try doubling this estimated capacity. All right, so we have to wait a round trip because, any ideas?
We have to know how many got dropped.
Yeah, we don't know anything until we can get some acknowledgements back from the end host. No one tells us along the way. So yeah, not much choice there. Okay, so now we double it, and then another round trip time, we double it again. And so now at some point, we start losing packets. Okay, repeat until we lose some packets. Go back one. Right, so we've doubled it too far, And then, okay, so we maybe half it again, and then we can more carefully try to reach the final capacity. So we go something like from here to, I'm drawing capacities here. This is 1, and then to 2, and then up 4, and then up 8. Oh, and then we lost the packet going at this rate, right? If you imagine here's, oh, great. So here's time, and over here is our estimated capacity. So here's a round trip time, something like 4 of these. It's a round trip time, so the next time we go twice as fast, and then we go 4 times as fast, and we try going 8 times as fast, and there we drop the packet. So, all right, so then we go down to back to 4, and then maybe we try a little more conservatively, so we just go linearly up until we reach some point where we drop a packet again. Okay, so something like this, so aggressively first ramping it up, and then carefully once we've sort of achieved the limit we're interested in. It's probably a good design. This is actually what TCP does. I thought we'd try that. Let's see, we'll give that a shot. No, let's do that New Zealand one again. I think they had a picture that was really slow on the front page. Yeah, this one. Okay, never mind. Okay, so wget just fetches the image. But before we do that, that's the HTTPS, so I thought I would just capture that traffic, and then we'll get some timestamps, see what a plot looks like, something like that, see if it works. 443 is the SSL port, or HTTPS port. So we'll just capture that and stick it in a dump. Okay, let's get it. Oh, it's beautiful. Look how slow that is. Great. And here they are. So let's see. Is there no timestamp? I was hoping there was a timestamp. This is the timestamp. Okay, good. Okay, we'll need to translate that somehow. Oh, I guess we can just go with the seconds, and these are microseconds. Yeah. So if we just ignore the minutes, we'll be good. Let's do that. Now it looks like that, and I'm interested in just a second. So was it 2? No, it's 3. Okay, so these are the timestamps of the packets, right? Timestamp in seconds and packets. Maybe we should go the other way around. Can we do that? In fact, I don't know how to do that. Never mind, we'll just take it this way. So you kind of see in the beginning, we didn't send a whole lot. Let's zoom in a little bit on the first 100 packets. Right, okay. So looks like, well, we got a fair number out there. I wonder if this was something else from my web browser. There's a decent chance of that. Let's just to make sure we're not telling you lies here. 132. Yeah. Oh no, 180. Oh, that looks pretty okay. Looks like all we're talking to is this guy. Okay. I'll just cut that out too. Okay. All right, so now we only have communication with this New Zealand server. I think we lost a few packets in there. Okay, so it looks like we started out with 3 packets. What might that be? Pretty fast, there were 3 packets. Probably our SYN-ACK, right? Our SYN and our ACK and our SYN-BACK. This is, I don't know why they're so close back to back though. All right, in general, I think we'll have to look at the details a little bit later, but in general what we see is we sent just a few packets, then we had a wait, right? And then we sent a few packets and a wait. Here we must have lost something in between here. We must have lost a packet on the way, because otherwise we wouldn't be this careful. Right? Such a long wait. It's like a second.
I think it said 0 packets dropped when you were.
Huh. Well, in that case, maybe they have a really slow web server or something. I don't know what's going on over there. But we got a whole second that we're waiting over here. And then, now finally we start to kind of get an idea of what's happening here. So we go 6 packets. Well, these are in both directions. We get the axe and the, maybe I should cut it down so we go in just one direction. Let's do that too. So we want the ones that go like this, right? No, actually the other way is what we're interested in. Whatever's coming to us, of course. Right. All right, so it's this one. Any packets that are coming from the server to us, we're not too interested in our request. That's what it was. Okay, so we saw the little request first, right? And then the server responds after a little while with its, here, this is the request. And then the server responds with its long transfer. There it is. Okay. Okay, so I'll just grab the response. Okay, that's a lot better. So this would be the initial handshake, and why it's so fast, I don't know. But then we're sending 1 packet, a couple of packets, and then we've got many and even more, like we're doubling it up relatively fast. And at some point, we've figured out what the capacity is of this link. So you see, we send a whole bunch of packets back to back, and then we wait for a little while until we get the axe for that, and then we send a whole bunch of new packets back to back. Right, over and over, and the length of this is about the same. Maybe it grows a little bit, right? But it's not very aggressive. Here it's aggressive. It starts with just a few, then more, until it kind of calms down. Okay, so that's what we want to do on this link. But that gives us sort of a capacity estimate for the link if the environment doesn't change at all. Right? The environment changes all the time, however. So if another flow comes in, so we started out with this flow and it decided to go at this rate. Let's see now. Let me change this. You reduce this one to be the same thickness as the end. Yeah. Yeah, okay. So now we're transmitting over this link at the full rate of these two. The thicknesses are kind of the available rate on these links. And now suddenly starts a new connection. All right. So this source wants to transmit to this destination. And ideally, I think we would want the two to get the same capacity. right? Assuming, actually, why don't we change it around like this instead? Yeah, that's good. And one more. Right, so now we have two flows, and they're competing not for the end links, but for this link in the middle. If we started out with one flow, it would have reached a capacity, much like in our plot, or saying, okay, we can fill the pipe this way. But then comes the other flow and starts transmitting, and now we need to adjust our rate somehow so that they both get roughly the same speed. Right? That would be nice. We call it fairness. It's hard to get perfect fairness in the internet, but at least per flow fairness on any given link, something we try to achieve. So how do we get there? Any ideas?
Maybe the one that already knows the capacity communicates with the new guy and tells him, here's
Ooh, nice.
going to give a path.
Right, okay, so source 1 here magically detects that source 2 and another part of the internet wants to talk to destination 2 and tells them this link has this much capacity. Good work, but it is a little... The middle links here could be used by lots of different nodes. It could be sitting somewhere in the middle of the Pacific. We don't necessarily want to be bothered with those links. It'd be better if we didn't have as much coordination. Any other ideas? I think a relatively obvious one would be for this router here to say, like, you know, this is full up. You have to send at half the rate, and I'll tell the other one to send at half the rate. But the internet doesn't work that way. We don't have the routers do much work for us. So, any other ideas? Yeah.
Once you notice that you start dropping packets because like the buffer filled up and stuff, so you just slow down the rate.
Okay, so this guy is already sending at the full rate. Source 1 is sending at the full rate, so the buffer is full. Now comes source 2. Sends its first packet. And maybe it gets in here. Maybe not. Maybe it does. If it doesn't get in here, then it'll have to try even slower. That's not so great, but if it does get the first packet in, that's good. Now source 1 will lose a packet instead. So source 1 is sending at the full rate. It'll reduce some because it lost a packet, and source 2 gets to get one packet through. Right. And then next time, source 2, because it got one packet through, maybe it sends 2 packets. But now again, the queue is full, and now source 2, it got lucky last time. Now it has to get twice as lucky because it's sending 2 packets in. It's at a disadvantage because it's sending at such a low rate, and this other one is sending at a high rate. It'd be better if source 2 wasn't losing any packets at all. Right? Because it's sending at a really low rate. If this is going to be fair, it ought to be the source that's sending a lot loses all its packets until it's kind of transmitting at a similar rate. This is something that's actually provided by some routers. It's called fair queuing, which is pretty nice. So then the router keeps a separate queue for every flow pair, for every flow like this, and then runs round robin between all of those queues. Problem is, in a core internet router, you can easily have 100 million queues because you have lots of these low rate flows going through the same router, and so it's not practical there. We have a much easier solution. Has to do with the congestion control again. So basically, anytime you lose a packet, actually, let's update this a little bit. Let's call this slow start. With TCP, it's called slow start not because it's ramping up slowly, but because it starts really slow. right? It starts with just one packet, maybe a couple, depends a little bit on configuration. But basically you start with a very slow rate, and then you quickly ramp up to what seems like a reasonable rate. And then you go back to half, and then additive, the rest is called additive increase, right? So every round trip, we add maybe one more packet to the estimated capacity. And then the next step is multiplicative decrease. Means lose a packet, drop by half. All right. So if you lose a packet, and this is actually provides a really nice advantage now to source 2. Source 2 is starting at with one outstanding packet. Right? Congestion window is what it's called. Like how many packets do we have outstanding at any given time? Source 2 starts with a small congestion window, and source 1 here has a large congestion window because it's been running. So when source 1 loses one packet because source 2 traffic is coming in, it immediately drops its congestion window to half. So now it's sending half as much capacity. This half, now that means that the queue will quickly shrink to something relatively small. We're not sending as fast as the outlink can handle. Source 2 can kind of ramp up relatively aggressively until it gets to something similar to source 1. Okay, so now both of them are sending at about half, and they're both ramping up, right? I should go like that. They're both ramping up, and then one of them loses a packet and drops down to half, right? The other one keeps ramping up, and then it loses a packet, and the other one has ramped up a little. So they go kind of up and down like this, right? So with TCP, or at least, yeah, TCP is the state of the art here. You don't have a steady rate. You're kind of alternating between something that's a little too fast and something that's a little too slow. Okay. Yeah, we're out of time, as you can tell. Next time, I think we'll try to look at some examples of how this works in practice with a few different flows. Let's see what I can manage. And then we'll start looking at sort of error handling in TCP as well. Oh, yes. I woke up one morning and way early, and I had this thought, maybe I didn't tell them about this for DNS. The DNS, we did this whole DNS thing with resolution, a client that resolves everything. And your computer usually doesn't do all that work. It goes through a DNS resolver. Did I mention this? There's a server, a local server, whatever you configure in your network settings sometimes. It says like a DNS server. Your computer sends a request to that one. It does all the work for you. And then you get the answer back. So usually your laptop isn't involved in what we were doing for the homework. That's done by a DNS resolver. That's your local DNS server. That's all. Have a good weekend. See you Monday.